Welcome to the Deep Dive. We're the show that really gets into the nitty-gritty of new research for you.
That's right. Tailored insights from studies that matter.
And today we are diving deep into, well, the absolutely electrifying world of biathlon.
Yeah, it's pretty incredible when you think about it.
Just imagine the demands these athletes face. You're pushing your body to its absolute limit, skiing incredibly hard, and then...
And you have to stop, calm everything down your heart, your breathing, and take a precision rifle shot.
It's this extreme mix of pure aerobic power, muscle endurance, and just pinpoint mental focus.
It really is. And it brings up a huge question, doesn't it? How do they train for that edge?
Exactly. How do you gain that competitive advantage without completely burning out or breaking down?
It's a constant search, that optimization puzzle, always looking for the best way to train, maximize gains, minimize the downsides.
And that leads us right into today's deep dive. We're tackling a really specific question.
Can training in simulated high-altitude conditions, hypoxia, actually boost performance and cut down fatigue in young biathletes?
To get answers, we've got our hands on some genuinely groundbreaking research. It's really fresh.
Very new, yeah.
Our source is an article called Effects of High-Intensity Interval Training in Normobaric Hypoxia on Aerobic Performance and Exercise-Induced Motor Performance Fatigue in Young Biathletes.
Quite a title, but it tells you exactly what they looked at.
It does, and it's from a big team. Aleksandra Żebrowska, Marcin, Sikora, Rafał, Mikołajczyk, Dagmara, Gerasimuk, Mabliny, Thuany, Katja, Weiss, Knechtle, and Barbara Hall.
A solid group of researchers there.
Published online, Journal of Sports Science and Medicine. That's volume 24, pages 613 to 625. The DOI, if you want to look it up, is 10.52082 JSSM.225.613.
And you mentioned it's new.
Just published online, September 1st, 2025, so really cutting-edge stuff.
Definitely.
So our mission today is to take all this science and distill it down, make it accessible for you so you can understand how this kind of training impacts these young elite athletes.
All right, let's unpack it then. First, maybe we should set the stage a bit more. Really talk about biathlon itself.
Good idea. It's an endurance sport, fundamentally. Athletes are skiing anywhere from, 6 to 20 kilometers?
Yeah, and with multiple shooting stops mixed in. So it's not continuous effort.
Right, and obviously how fast you ski matters, how accurately you shoot matters, but increasingly it seems like overall aerobic capacity
And just sheer physical and mental toughness
are becoming maybe the deciding factors, being able to stay precise even when you're completely gassed.
Which brings us to HIIT, high-intensity interval training. It's become such a cornerstone in athletic prep.
And for good reason, right? It works.
Oh, yeah. HIIT is known to trigger a whole host of physiological adaptations. Better breathing efficiency, improved heart and blood vessel function, what scientists call cardiovascular hemodynamics.
Basically, your body gets better at delivering oxygen.
Exactly. And that helps with sustained performance, but also with bouncing back quicker from things like acidosis, that muscle burn you get.
Lactic acid buildup. Yeah.
So HIIT is key. But then this study adds another layer, hypoxia, training in thin air.
Now, high-altitude training isn't new. Athletes have done that for ages. But this study looked at something specific, normobaric hypoxia.
Right, so normal air pressure, like at sea level, but they reduce the oxygen content in the air the athletes breathe, usually in a special room or tent.
Simulating altitude without actually going up a mountain.
Precisely.
Right.
And the theory, the hypothesis, is that the simulated altitude can kickstart even more beneficial adaptations. Sort of tricks your body into becoming more efficient with the oxygen it does get.
Okay, so that's the theory. How did they actually test it? What was the study design like?
They used a really smart approach, a randomized controlled crossover design.
Okay, break that down. Randomized controlled crossover.
Right, so randomized means the athletes were assigned to the order of conditions randomly. Controlled means they compare the hypoxia training to a control condition in this case, training in normal air. And crossover.
That's the clever bit, isn't it?
It really is. Crossover means the same group of athletes did both types of training, the hypoxic and the normal oxygen, just at different times.
So each athlete acts as their own comparison point.
Exactly. It makes the results much more robust because you're not comparing two different groups of people. You're comparing how the same person responds to different training. It helps eliminate individual variability.
Smart. And who were these athletes?
They had 12 young biathletes. 5 males, 7 females. Average age was around 15, nearly 16 years old.
So young, developing talent.
Definitely. And they weren't beginners. They all had at least 3 years of solid training behind them and were part of the Polish Biathlon Association's national team. Elite potential.
Okay, so we've got the who, What about the what? What did the actual training look like?
It was structured into 2 blocks, each lasting 3 weeks.
One block in the simulated altitude.
Right, Normobaric hypoxia, simulating about 2,600 meters. The oxygen level they breathed was reduced to 15.2%.
And the other block?
It's normal air, Normoxia.
And crucially, they put a 3-week washout period between the 2 blocks.
To let the body reset, so effects from the first block didn't mess up the results of the second.
Precisely. Cleans the slate physiologically.
Makes sense. And the sessions themselves. Intense.
Oh, yeah. 3 days a week, 80-minute sessions each time. Pretty demanding.
What kind of exercise?
It was a mix designed to mimic biathlon. First, 5 rounds of 4 minutes running at 80% of their peak oxygen uptake.
So pretty hard running.
Definitely.
Yeah.
Followed by 3 minutes of active recovery, like light jogging or walking.
Okay.
Then they moved on to upper body work. 4 rounds of 1-minute arm cranking at 60% of their peak power.
Mimicking the pulling action, maybe? Or rifle stability?
Yeah, targeting those upper body demands with
fair.
2 minutes of rest between those arm cranking bouts.
A well-rounded biathlon-specific HIIT protocol.
That was the goal.
Okay, so they put these young athletes through these intense hypoxic and normoxic training blocks. What were they measuring to see the effects? They gathered a ton of data. Before and after each 3-week block, they did comprehensive testing.
Like what? Performance stuff.
Yep, key aerobic performance markers. Things like VO2 peak, your maximum oxygen uptake, and also VO2 at lactate threshold, which is a really important measure of endurance efficiency. Peak power output, too.
And what about the hypoxia-specific markers? Did they track those?
They did. They look at things like HIF1, hypoxia-inducible factor 1 alpha, which is a key regulator your body uses to respond to low oxygen, and VEGF, vascular endothelial growth factor.
VEGF, that's involved in building blood vessels, right?
Exactly. More blood vessels could mean better oxygen delivery. They also measured stuff related to muscle damage and recovery.
Ah, like creatine kinase.
That's CK.
Okay. Myoglobin. Those tell you if muscles are breaking down.
Precisely. CK, myoglobin, lactate dehydrogenase, LDH, even troponin, indicators of muscle stress and damage.
And inflammation. Intense exercise can cause inflammation.
Yep, they measured inflammatory markers like interleukin-6, IL-6, TNF-alpha, and TGF-beta. These give you a snapshot of the body's immune response to the training stress.
Wow, comprehensive. Anything else? Blood work.
Standard hematological stuff. Hemoglobin HB, hematocrit, HTT, red blood cell count, RBC. All related to oxygen carrying capacity in the blood. And also antioxidant status, how well the body's defense systems are handling oxidative stress.
Okay, they measured a lot. So after all that, what were the big results? Did the hypoxia make a difference?
It certainly did. And this is where it gets really interesting for performance. The study found a significant effect of the hypoxia condition on VO2 peak.
Their maximum aerobic capacity improved more with the hypoxic training.
Essentially, yes. VO2 peak was significantly higher after the hypoxic training compared to before it started. While the direct comparison between hypoxic and normoxic training improvement didn't hit statistical significance for VO2 peak itself, the effect size was large, suggesting a real physiological impact.
Okay, so a strong trend there. What about the lactate threshold measure, VSHO-LT? You said that was important.
Hugely important. And here, the results were even clearer. VSHO-LT showed a significantly greater improvement after the hypoxic training compared to both before hypoxic training and compared to after the normal oxygen training.
Wow. So translate that for us. What does that mean for the athlete?
It means, essentially, they could sustain a higher intensity of exercise ski faster before fatigue really started to bite, before that lactic acid started accumulating significantly. For an endurance sport like biathlon, that's a massive advantage.
Being able to push harder for longer before hitting the wall, game changer.
Absolutely. And peak power, P-peak, also went up after both types of training, which shows the HIIT itself was effective. But that extra boost in aerobic efficiency, especially at threshold, seemed linked to the hypoxia.
So why? What's happening under the hood physiologically?
Well, the researchers suggest it's linked to those cellular adaptations we talked about. The hypoxia seems to trigger mechanisms that help muscles use oxygen better.
Like the VEGF finding.
Exactly. They found significantly higher levels of VEGS after exercise following the hypoxic training block. That points towards increased angiogenesis. The body's starting to build more capillaries, more tiny blood vessels.
More roads to deliver oxygen to the working muscles?
That's the idea. Better plumbing for oxygen delivery.
Okay, so improved performance is key finding number one. What else? You mentioned muscle damage and fatigue.
Right. because making athletes faster is great, but you also need them to recover well and not get beaten down by the training. Intense exercise does cause muscle fatigue and some level of damage. Those biomarkers tell us about that.
And did the hypoxic training help with that side of things?
It really did. This was another major finding. The study showed that the hypoxic HIIT actually had a protective effect against exercise-induced fatigue and damage compared to the normal oxygen training.
Protective. How did they see that?
Through those biomarkers. Post-exercise levels of myoglobin and creatine kinase, those muscle damage indicators were significantly lower after the hypoxic training sessions compared to the normoxic ones.
So less muscle breakdown occurred during the hypoxic workouts, even though the intensity was similar.
It seems so. Myoglobin was also significantly lower after the whole hypoxic block compared to before it started. It suggests the body adapted to handle the stress better under hypoxic conditions.
That's huge for recovery and maybe preventing overtraining over a long season.
Absolutely. Less damage means potentially faster recovery, less soreness, ability to train consistently.
And what about inflammation? Did hypoxia affect those markers like IL-6?
Yes, another really interesting finding. The inflammatory response was dampened after hypoxic training.
Dampened how?
Post-exercise levels of several pro-inflammatory cytokines were lower after the hypoxic block. IL-6 was lower compared to before and compared to after the normoxic block. TNF-alpha and TGF-beta were also lower after hypoxic training compared to normoxic.
So the body's inflammatory reaction to the hard workout was less severe in hypoxia.
That's what the data suggests. It implies that hypoxic training might help mitigate that immediate inflammatory spike you usually get after intense exercise.
Which, again, could mean faster recovery, less systemic stress.
Potentially, yes. It's all interconnected: less damage, less inflammation, better recovery, reduced fatigue.
Did they see anything significant with the antioxidants? You mentioned they measured that too.
That was a bit more nuanced. There wasn't an overall significant effect on total antioxidant status, but the oxygen conditions did significantly affect levels of one specific antioxidant enzyme, glutathione peroxidase, GPX. And the combination of oxygen condition and training affected levels of reduced glutathione, GSH.
Okay, so maybe not a massive system-wide change, but subtle adjustments in specific parts of the body's antioxidant defense system.
Exactly. It hints that hypoxic training might be fine-tuning how the body deals with oxidative stress, even if it doesn't boost the whole system overall in just 3 weeks.
Right. Okay, so we have improved aerobic performance, reduced muscle damage, and a moderated inflammatory response. Pretty compelling results.
Definitely. But like any study, there are nuances and things to consider.
Let's get into those. What about the blood adaptations? Did they see big changes in hemoglobin and red blood cells, which is often the classic goal of altitude training?
That was fascinating, actually. Hemoglobin and hematocrit did increase significantly after the hypoxic training compared to before, and also compared to after the normoxic training.
So their blood got better at carrying oxygen.
Well, yes and no. Capacity seemed to increase based on HB and HTT, but interestingly, the actual number of red blood cells didn't significantly change over just 3 weeks.
Huh. So how did hemoglobin and hematocrit go up if red blood cells didn't?
The likely explanation, which the researchers point out, is probably a reduction in plasma volume.
Ah, so the liquid part of the blood decreased slightly, making the red cells and the hemoglobin within them more concentrated. A fluid shift.
Exactly. It's a faster adaptation than actually producing brand new red blood cells, which is called erythropoiesis, and usually takes longer, weeks or months. So an immediate adjustment rather than a long-term production change in this time frame.
Interesting. It shows how the body adapts quickly in different ways. What about that HIF-1 molecule you mentioned earlier, the hypoxia sensor?
Yeah, another slight puzzle. Serum levels of HIF-1 didn't actually show significant changes in this study, despite the hypoxic stimulus.
Even though it's supposed to be the master switch for hypoxia adaptation.
It is known as a key regulator, yes. But physiology is complex. It could be that the timing of the measurement missed the peak, or that adaptations were happening more locally in the muscles rather than showing up strongly in the blood serum, or that other pathways were more dominant in this specific context.
Right. It just highlights that we don't always see textbook responses, and adaptation is complicated.
Absolutely. And it leads into the limitations the researchers themselves acknowledged.
Every study has them. What were the main ones here?
Well, the sample size was relatively small, 12 athletes. That's decent for this kind of intensive physiological study, but it meant they couldn't really look for differences between the male and female athletes, for instance.
Gender-specific effects might exist, but they couldn't test for them here.
Right. Also, Measuring those inflammatory markers, the cytokines, only right before and immediately after exercise gives you a snapshot, but maybe doesn't capture the full picture of how inflammation might resolve or change over the hours or days following the workout.
You might miss longer-term effects, positive or negative.
Potentially. So future research could look at that more closely.
And what about the duration? 3 weeks is pretty short for some adaptations.
It is. The researchers suggest that longer periods of hypoxic training, maybe going beyond 3 weeks, might be needed to see those more substantial classic altitude adaptations, like a real increase in red blood cell mass.
So more research needed there too.
Definitely. Confirming long-term benefits and really nailing down all the specific mechanisms would be the next steps. But what they found in just 3 weeks is already quite significant.
Okay, so let's try and wrap this up. What are the core takeaways from this deep dive?
I think the main message is pretty clear. Even a relatively short 3-week program of high-intensity interval training done in simulated altitude, Normobaric hypoxia, gave these young elite biathletes a significant boost.
Boosted their aerobic performance, particularly that crucial VO2 at lactate threshold.
Yep. And just as importantly, it seemed to offer a protective effect. It helped reduce the amount of muscle damage from the intense exercise and kept the inflammatory response in check compared to training in normal air.
Less fatigue, potentially faster recovery.
That's the implication.
So this research offers some really valuable insights, doesn't it? Not just for coaches working with elite biathletes.
No, I think the principles could be relevant much more broadly. Anyone interested in enhancing athletic performance, or even just understanding how incredibly adaptive our bodies are, can learn something here.
It really highlights the science behind pushing limits effectively and smartly.
It does. Precision matters in training.
Now, we've covered the key findings, but there's obviously a lot more detail in the actual paper.
Oh, absolutely. We've really just scratched the surface. To get the full picture, the detailed methods, the statistical analyses, the deeper discussion, you really should check out the original article.
That was Żebrowska and colleagues in the Journal of Sports Science and Medicine.
Right. You can find it easily online using the title, or the DOI we mentioned earlier, 10.52082 JSSM.2025.613.
We highly encourage you to do that if this topic sparked your interest.
Definitely worth the read.
And if you found this deep dive useful, please make sure you follow our channel.
And turn on those notifications. That way you won't miss our next exploration into fascinating research and maybe some surprising facts.